networks, Facebook and Twitter, and our own website. Is that okay with you?
Okay.
Okay, fantastic.
Yeah.
Right. Okay, thanks for coming. It's a great honor to present Ray Smith. Comes from California. Well, it's a nice climate here as well.
Very similar.
Very similar. So with Ray, well, I kind of know him for quite about 20 years now. Since he was in Hewlett-Packard, he started working on OCR for, well, he's been working on that for as long as I remember. Since the 90s, basically.
Since the 80s, actually.
80s. Wow, yeah, I'm pretty young for that. Well, he was developing OCR systems in Hewlett-Packard, in Bristol at the time. He went on to re-architect Omnipage at some point, and then Tesseract became open source. It was acquired by Google. Google made it open source, actually, and it was used for the Million Book project as well.
That's right.
And now he's doing text reading in different contexts, not only in printed documents. Although Tesseract is still good and alive, and there's going to be a new version that hopefully Ray will tell us about soon, where some new network-based technology, LSTMs, etc., is fully integrated with TensorFlow, so that's going to be an interesting thing to look into eventually. The floor is yours. Thank you very much for coming.
Thank you. Let me get this thing on the road here. So thanks for the introduction. I was going to go over some of that myself if you didn't. Next Monday, it's going to be 11 years since I joined Google. It doesn't seem like 5 minutes, honestly. I spent the first 6 years there working on the books project, working on Tesseract, which is what I'm probably most known for. For the last 5 years, I've been working on Street View. And this talk is going to be mostly about Street View and how Street View works together with maps. Now, you've probably heard of Google Maps, and you've most likely heard of Google Street View. Thank you. Oh. But you probably don't know how they help each other. So I'll start with a bit of history of Street View. It launched in 2007 after I'd been at Google for a couple of years in only 5 cities in the US. Over the next couple of years, it spread over the whole of the US, followed eventually by most of the world. And this slide is out of date. It's covering 70 countries or more now, I believe. I was trying to find out exactly how many on the web last night, and it wasn't particularly easy unless I actually counted them individually. So, as I've already mentioned, Street View and maps work together to build maps. And the reason is we want to be able to have the best maps for our users. And something that we've discovered in getting the best maps is the old adage that if you want something done properly, you need to do it yourself. Right? So we have to develop our own maps, and we found the imagery in Street View very useful for doing that. However, it's not quite as simple as you might think. Our cars are equipped with cameras, they're equipped with GPS, and they're equipped with a few other things to help them know where they are. But if you just use the raw GPS signal inside an urban canyon where you've got huge buildings either side of you, you look up at the sky, you can't actually see very much of the sky, right? So you can't see very many GPS satellites. So you can't really get a very good accurate fix on your position that reliably. So as you can see here, if you just follow the GPS tracks along a particular, along a particular street, that was working. That one, right? It's not exactly a straight line. Yeah? So the other equipment includes inertial motion detection and wheel encoders, which help the car determine more accurately where it is when it's not got a good GPS signal. And with that and some pose optimization, we can get a much more accurate positioning of the car. So in theory, once you've taken a Street View photo, you know exactly where it was taken, you know what direction the camera is facing. So in theory, you can say anything in that image, I know at least what line it's on away from the car. And here's another example of a bigger area of downtown Pittsburgh where we've got improved pose optimization. So in order to convert from that imagery into maps, we need to do something other than just Street View. It's got to be street smart, as we call it. And to do that, we combine things that we have at Google. We've got lots of compute power. We've got lots of imagery. We've got reCAPTCHA and our own internal crowdsourcing platform. And then we have a lot of machine learning technology. Combine those together and we have good maps. So I said we want to make the best maps for our users, and maybe you don't really quite understand how images come into that. So say the user types an address, and we want to stick a pin in the map at the exact location of that address, not half a mile down the road, right? If somebody says, where's 1510 El Camino Real Mountain View, we want to stick the pin in the map in the right place. And we have images of the buildings on El Camino Real, and those images contain numbers. And we know exactly where the car was when we took the photo, and there is the image of the numbers, 1510. So if we can OCR that and determine that that is in fact the number of the building, not some other number, then we can tell that this is 1510 El Camino Real, and we can put it on the map. Right? That's the general idea. This is where we started. Now here's a few examples of some interesting building numbers. And you can see this is not a document OCR problem, right? These don't look anything like things that you find on documents. And you get problems like they're not placed very well, they're not horizontal. In fact, I think I've got another slide. Here we go. This is not what Tesseract was designed for. We don't have horizontal baselines, we've got bad broken outlines, funny fonts, and the patch around the number isn't necessarily brilliant either. So, how do we do it? Well, from a management perspective, it would be nice to say, okay, here's an image patch which we think contains a building number. Let's have a magic neural network and have it spit out directly the text for the number, right? Yeah, sounds brilliant. So that's what we did. We built a neural network to do just that, and we trained it on 1 million examples, and lo and behold, it works. You know, you take an AlexNet style convolutional tower, a few fully connected layers, and then output layers that are specific to each digit position and another one that says how long the number is. And bingo, works. In fact, it works so well that not all the time, it's not 100% perfect. Here's a few examples where it doesn't actually work. But you can understand why it's made these mistakes. This isn't a brilliant screen. And I'm not sure exactly what number that 184 is supposed to be, but it looks like somebody's painted black over the 3 in the middle of that number. I really don't understand what that one's about. But anyway, it's enabled us to find hundreds of millions of street numbers all over the world and surpassing human accuracy, we think. It's hard to tell, really, that you've surpassed human accuracy, but and we released a public data set of these numbers several years ago, and it's been pretty popular. And of course, since then, we've generated even more. You know, once you get the automated system that generates the numbers in the first place, you can bootstrap and generate even more, right? But this is just the beginning, right? This is just building numbers. There are many more things you can do out in the wild that will capture information that will help you build maps, like highway signs. And then in the city, there are directional signs and other interesting things. And we can take it even further than that. We can look at this grey space. We can even find a building, a storefront, right? And we can see where its address is, and we can see a few interesting things about it, what street it's on, what interesting names there are displayed in the window might give us some idea of what kind of shop it is. And then we can find other things like traffic lights, signs, other interesting stuff like that. But once you start looking for signs, you find them everywhere, right? And our cars drive and take multiple photos, and in an intersection like this, it's very easy to start finding 1,000 signs, instances from all the different images, from all the different signs, which is a bit of a problem. And we have total data overload. We've got billions of signs that we found all over the world, many of them of which have turned out to be real signs in a large number of classes. So what do we do about this? It turns out that if you start clustering them by knowing that geolocation I was talking about earlier, plus knowing that this sign looks exactly the same kind of sign as this other sign that we've got an image of, and knowing that they're in the same geolocation, you can start clustering them and saying, these are probably different views of the same thing. Right? Here you can see that they're pedestrian crossing signs, probably in mainland Europe somewhere, probably France, judging by the names. So, enter the French street name signs dataset. And this dataset is becoming public even as I speak. And this is basically what we're releasing and announcing at the International Workshop on Robust Reading on Sunday. So we've got 4 different images of the same physical sign. They could have been taken at different times, possibly all from the same run as the car went past the sign. And then we've cropped them all to the same size and stuck them all together as a tiled image. And then we've given you the truth text, which is the text we would expect to find on the map corresponding to those signs. Right? So as you can see in this example, the sign's all in capitals, but the truth text is not. It's canonicalized, normalized, title case. And here's a few basic statistics on the set. The images are all the same size. They are 4 150 by 150 images stuck together. giving up to 4 views of the same physical sign. If we had less than 4, then it will be padded out with noise to make it the same size. Each sign may contain up to 3 lines of text, like you saw on the previous one. There may be more lines of text, but some of those may be irrelevant. And I think I saw one sign that had 4 lines of relevant text. The vast majority of them are 2 or 3. The truth text is normalized, as I've mentioned, and we have over 1 million images in the training set, and there are 3 other sets as well. A validation set, a test set, and a private test set for organizing competitions. The image quality is not completely consistent. Sometimes you get this interesting effect where different times of year signs may be overgrown. Sometimes the privacy filter kicks in and thinks it's a license plate and blurs it for us. And then, of course, you get these obstructions like street light poles, that kind of thing, signs stuck in the way, and the quality varies. Sometimes they're blurry and sometimes they're clearer. But you get the idea. You've got 4 views of it to play with, right? So in theory, most of the time you can see everything by covering the 4 different images. I mentioned irrelevant text. I can't actually read the bottom text in there, but it's irrelevant. We're just interested in the name of the street. And we're not particularly interested in Charles de Gaulle's date of birth and death. We're really just interested in the name of the street. Okay? And here's an example of the noise that you get when there's only 3. Just occasionally, the clustering doesn't work completely as intended, and so you get these imposters included sometimes. Now, let me talk a little bit about how the data set was generated, seeing as I don't have any slides on it at all. There's 2 aspects to this. Where did the truth text come from? And how did we generate the data, the split into the 4 data sets? So the data set was created by a combination of OCR, reCAPTCHA, and our own internal crowdsourcing platform. And we basically went through a process of generate some truth, show it to our crowdsourcing platform users with the image. If they say it's correct, then it's good. If it's not, we go back and do something else to it until we get it correct. And through that process, we generated over 1 million, about 1.4 million raw samples, which were then segregated by latitude and longitude into, this group will go in the training set, then we'll have a wall in between them 100 meters wide, and then we'll have this group will go in the validation set, and then we'll have another wall, and then this group will go in the private test set, and then this group will go in the test set, making the images all from disjoint physical locations. But of course, a street may drive all the way through all of those different geometries. So then there's this post-processing step whereby you say, I'll take all the truth texts from all of the training set, and then I'll exclude anything in any of the other sets that matches that text. And then I'll take all the truth text from the validation set, and I'll exclude anything in the other 2 sets that includes that text, and so on to the end. So the total text string in each of the 4 sets is completely disjoint. This prevents you from cheating and using a word spotter, basically, because you end up with a 30% out of vocabulary problem in each of the other sets relative to the training set. And that's shown in these statistics. We've got 1 million images. We've got the order of 20,000 images in the other sets. And in the experiments I've run, the performance of any given system on those 3 sets is extremely close. So they're very representative, which I think is a good thing. So I think that covers that. Oh, I forgot to mention at the beginning, feel free to ask questions as I go along. Don't save them to the end. This is a seminar, right? That's the intention. There might be more questions as we start coming to the model. So the challenge of this data set then is, can you find those 3 lines of text on the sign? Well, can you even find the sign? Can you find the 3 lines of text on it? Can you OCR the text, get rid of the stuff that we don't need, title case normalize it, somehow combine information from those 4 images and ignore those imposters or the blurred or the obscured images? Now, you could engineer a solution that did that, right? Old-fashioned image processing, some old-fashioned pattern recognition, or you could even try and build something that did the whole thing end-to-end, right? So I had a go at solving this with Tesseract just to see how well it did. I had this idea of I'll detect the edges of the sign to get the rectangle and then correct the projective distortion of that rectangle. And then it will be possible to run pretty much vanilla Tesseract within that rectangle. It will detect the text lines and read the text. Just a little bit of conversion, a bit of merging of the results by confidence, and you should get some answers. And I did, but they weren't brilliant. I only got low 20s word recall, and 95% of the total string was wrong. Or rather, there was an error in the entire string 95% of the time, right? So, and this is even using new Tesseract. I had a look at some of the problems. I don't have any slides to show you of the problems. But most of the time it seemed to be the text line finding that was letting it down. It would do stupid things like put 2 lines of text in one text line, and then of course it's bound not to get that right. But anyway, really, the point of this was, as we did before with the numbers, what we would really like is a magic neural network that would take this image and spit out this text. The question is that possible? And it turns out the answer is yes. And here is the entire model on one slide. I don't expect you to understand it from here, but this is just so I can summarize it and I can go through the individual parts on separate slides, right? So we've got the input image over on the left here, and the first thing that happens is they are detiled, so they become separate images, and they can be processed separately through most of the network. So then we've got a couple of layers of convolution and max pool. We've got a really complicated thing that I'll explain later that involves summarizing LSTMs to find, it's designed specifically for finding the 3 text lines, basically. And then we've got some forward-backwards LSTMs to normalize the text so that the 4 different images can be aligned. And then there is a final combination of those 4 images and the output layer. So before I go into that, well, here is the full detail of the model for the numerically inclined. There's a total of 2.2 million weights and 1.3 billion multiply adds involved in this model. I'll come back to this slide. But first, a digression for background, just in case you've not heard of a summarizing LSTM, for instance, or even an LSTM, for that matter. So over 3 years ago, I started looking at LSTMs as being the new way for Tesseract. And I'd been given an example from Ocropus that was claimed to be better than existing Tesseract. So I had a look at it, and it looked very interesting and started working on it. And that model did something like what's on this slide. So the idea is you start with a rectangular piece of image for one text line, which you scale to a fixed height, being 48 pixels in this case. And then you run a bidirectional LSTM over that image, treating a single pixel strip, vertical strip, as the inputs. So it has 48 input values for each time step. And you have one LSTM runs left to right, that's the forward LSTM, and then you have another one runs right to left, which is the backward LSTM. And of course, the backward LSTM is implemented as a reverse the inputs, run a forward LSTM and reverse the outputs thing. Right, it's the way you do it. And then you combine the outputs of those two together and feed them into a standard softmax layer with number of outputs equal to the number of characters in the character set. And then it spits out something like what you see along the top here. And you train it using this connectionist temporal classification thing, which basically says you're allowed to output nulls most of the time, a no character symbol, a special extra symbol. And if you happen to output the same symbol twice in adjacent time steps, they get merged together into a single output. And to produce a double letter, then you have to explicitly put a null in between them. And then you end up with the desired output string. This is pretty straightforward, and it does indeed work really well if, and only if, the input is well normalized such that the baseline is in a consistent place and the mean line is in a consistent place. If you happen to get any kind of jitter on that image, it's screwed, because now it's going to see different features in different places in its input, because it's expecting the baseline to be at the 10th input or whatever. So this is exactly the result I saw. It has exactly the same problem as Tesseract does. If the baseline is misestimated, it screws up badly. If the x height is miscalculated, it screws up badly. And there you go. I've said it on the slide too. So, enter the summarizing LSTM. In a conventional, regular, one-dimensional LSTM, you slide it in one direction over a series of inputs called the time steps, and it produces an output at each one of those. Right? Always one for one. Now, if you ignore all of the outputs except the last one, and you only backprop through that output, that last output, then you force it to create some kind of summary of what it's seen. Right? This is very similar to the idea in the encoder-decoder translation idea with LSTMs. Right? You force an LSTM to look at some input and then produce a single summary snapshot of its output. And then you feed that into some kind of decoder, and that will decode it into another language. That's how translation works. So same idea, except this is with images. So I've got a two-dimensional picture now. Think of the green squares as being the input pixels. They're not necessarily pixels anymore because it's been through several layers of neural network already. And then you run one of these summarizing LSTMs vertically down each pixel column independently and ask it to produce the single output. So now you have a 1D sequence running horizontally across the image. And it has produced some kind of summary of what it's seen in that vertical scan. Okay? No questions? Yeah?
But any rotation out of the minimal, this should be sensitive, right?
Yes and no. Just as the conventional one-dimensional scanning LSTM is completely insensitive to left-right movement, right? The the summarizing LSTM can be insensitive to vertical movement. And if you then feed this output through a horizontal LSTM, that's sensitive to the left-right movement. So between them, they're relatively insensitive to most transformations. Rotation slightly, but if you do a large rotation, then yes, it's going to be trouble. Okay? So, it's far better to use one of these summarizing LSTMs and work in 2D than it is to do that 1D thing, right? So you start, oops, wrong one. You start with a 2D input, and you now stick some conventional convolutional layer on the bottom, and then you run the summarizing LSTM running vertically down the image. It produces a summary of each vertical strip now with that shift invariance that you want. And then you put the output from that through either a conventional bidirectional LSTM, or you stack one that goes forward and one that goes backward above it and another one that goes forward above that. Then conventional softmax, same CTC, same output, better results. More invariance to skew, mispositioning of the line. You can make it ignore junk from adjacent lines. This is the network that's in the new Tesseract. And compared to the old Tesseract, which is starting to look a bit creaky, it produces tens of % reductions in the error rates across all languages. It's really good. It's coming out soon, I promise. Right. Back to the FSNS dataset. And this model which I've called STREET, which stands for Street View TensorFlow Recurrent End-to-End Transcriber. Yes. So, the convolutional layer. We break the 4 tiles into individual tiles. Oh, we've got the tensor dimensions at the top here. It should help you follow it, right? So it's 4-dimensional. You've got a batch. The y size, the x size, and the depth in that order, right? Y and x are reversed, and it's a TensorFlow convention. Okay? It's because you don't have to transpose the image when you stick it into the tensor, right? So we start with this 150 by 600, and it becomes 4 150 by 150s, still in RGB space. And then we have a 5 by 5 convolution, 16 outputs, followed by a traditional 2 by 2 max pool, and another 5 by 5 convolution, again with 64 outputs this time, and a 3 by 3 max pool. And between them, they have now reduced the output to 25 by 25, 64 deep. Okay? A batch of 4. This bit's fairly straightforward, especially if you've seen convolutional neural nets before. Now, the big one. That 25 by 25 output is now triplicated, fed into 3 different inputs. Now, at the top here, we've got vertically summarizing LSTMs that scan upwards. Okay? If you think about it, they're looking at this sign with 3 lines of text on it. The last thing they see is the top line. The idea is, give me the content of the top line and forget what you saw before that. The output from those goes into a bidirectional LSTM. And we have the existence proof from Tesseract that can read an entire English text line with no difficulty, right? So the assumption is, in this design, that the summarizing LSTMs will find the top text line, and then this will read it, generating 256 outputs because it's got 128 states and it's bidirectional, so there's two of them to stack together. I'll do the bottom line next. We have a summarizing LSTM working downwards with the idea that it picks up the bottom line of the three. Again, it goes into a conventional bidirectional LSTM, exactly the same as the top line. The middle one's a bit more complicated. How do you get the middle line? Well, overkill, I thought. Let's have a summarizing LSTM that goes upwards and another one that goes downwards. We'll take the two and combine their results. And that will give the middle bidirectional LSTM the best possible chance at reading the middle line. Why not? Works. So that's what we've got here. We've got two vertically summarizing LSTMs working in opposite directions. You can think of it as a bidirectional summarizing LSTM if you like. And those outputs are then depth concatenated and fed into a bidirectional LSTM. Now the outputs of the three bidirectional LSTMs are concatenated in the x direction. So in theory, the top one has read the top line. I'm going to put this down. The top one's read the top line. The next one's read the next line, and we stick that to the right of the top line. And then the other one's read the bottom line, and we stick that to the right of that. So now we've got a single strip, hopefully with the text of the three lines stuck end to end. Right? You know it makes sense. Any questions on that? I know it's the most complicated bit. Yes? Yes.
The question is, why did you choose the name instead of Gradle, because it's becoming more standard now?
Habit.
Okay. And the other thing, what is, do you normalize it for concatenating, or you just concatenate directly? L2 norms of the vectors before?
No, they're just concatenated. So now, let's have a recap. We've got, in theory, we've got the three text lines stuck end to end into one long strip now. But we've got four independent shots of this sign. So now we need to stick them together somehow. But because they're taken from different viewing angles, the text may be in a different position. Right? You can't say, oh, I'll take the fifth pixel from the left and combine that with the fifth pixel from the left in the other image, because it might not correspond in space on the sign to the same letter, right? So how do you combine those four different views? Well, okay, overkill again. We've got a left to right LSTM with a right to left LSTM stacked on top. Now, this enables, so the left LSTM can transmit things to the right, right? It can't see into the future, but it can see into the past. So a left to right LSTM can shift things to the right. And a right to left LSTM can do the opposite, can shift things to the left. So the simple hypothesis of these two layers is, between them, they'll be able to normalize the position of the text so that it lines up with the text from the other layers. Even though it's doing it blindly and doesn't have a view of the rest of the images, it's going to put things in a normalized position because I say so, right? That's what I want it to do. So having done that, we can take the four independent views, depth concatenate them, apply a bit of dropout because you want it to learn to deal with this problem of sometimes things are noise or sometimes they're wrong, and then shove that into the final left to right LSTM. Having done that, we have a conventional softmax layer, and it spits out the text. Train it with CTC, and it spits out text. That's all there is to it.
Do you have any language model somewhere?
The LSTMs have the language model built in. They make their own up. I have integrated this with Tesseract. Right, so you can run it through the Tesseract beam search. And it achieves a tiny improvement. It's not huge, but it is an improvement.
So you have a notion of where you are in this studio dictionary, the nature space that you have around there. Would that make any sense, or is it irrelevant?
It might. It would help, probably. But that isn't the objective here. The objective is to do open-ended OCR because we're building a map from scratch here. We're not trying to rely on any other map database because we want to build it clean. For the numerically minded, we're back to the list of layers and their sizes. Now, just in case you didn't think the diagrams were complicated or clear enough, here I have a reduction of all of that to a string. Right? Now, the idea is that you want to be able to experiment with this quickly. And you don't want to have 500 lines of Python code and have to fiddle around with that in order to experiment with, well, what if we add another layer in here, or change the size of this layer, or get rid of that layer there. Right? You want to just be able to change a few characters, and this is what this achieves. Within a few characters, it describes each of those operations that I've shown in those fancy diagrams. Right? And I'll go through and explain each one of these individually for you so you can get some sense of what this language is like. So first of all, we have the input specification. This is just the dimensions of the input tensor. It's a batch of one, it's 150 high, it's 600 wide, and it's RGB. Okay? Pretty simple. The square bracket indicates a series of layers until the ending square bracket. And then we have this horrible expression here, which is a generic reshape. This is how the input is untiled. Right? What it says is we'll take dimension 2, which is this one, we'll split it into 4 by 150, and the 4 goes to dimension 0, which is the batch, and the 150 stays in dimension 2, which is where it started. It's the X dimension. Okay, that basically untiles it and says I've now got 4 150 by 150 images instead of the input. Then we have a convolutional layer with tan H, which we've established is by habit only, and it's a 5 by 5 with 16 filters. And then we have a max pool, which is 2 by 2, followed by another convolutional layer with tan H, which is 5 by 5 and 64 outputs, and a 3 by 3 max pool. You see, it's pretty straightforward once you get the hang of it. And you can specify other letters here to get the ReLU that you desire, right? If you wish, you can say CR for ReLU. Or you can say CL if you want linear, CS for sigmoid, and CM for softmax. So the output of that is then fed into this parenthesis for parallel. The following units will be executed in parallel, meaning they take the same input, and their outputs are depth concatenated. We have a series of layers, which is LSTM, which operates in the reverse Y direction and summarizes with 64 elements, 64 cells. And that is followed by an LSTM, which is bidirectional in the X direction with 128 elements. And that's the end of that sequence. Now we've got the next one, which is the middle, the LSTM bidirectional in the Y direction, summarizing 64, and an LSTM which is bidirectional in the X direction with 128 cells. Then we have the bottom line, which is LSTM running forward in the Y direction, summarizing with 64 output cells, and an LSTM which is bidirectional in the X direction with 128 units. And that's the end of the parallel section. And then we have another reshape. Because the parallel stacked those three parallel things in their depth direction and we wanted them in the X instead, we've got to fiddle with the output. So we have to take dimension 3, which is depth, split it into 3 by whatever you had, and sending the 3 to dimension 2, which is the X direction, and leaving the rest in dimension 3. Finally, we have a forward LSTM in the X direction with 128 units, a reverse LSTM in the X direction with 128 units, and then a reshape. A reshape which takes that batch that we created at the beginning, splits it into 1 by 4, and moves those 4 into the X direction. Into the depth. So the final LSTM is seeing the output from the 4 tiles all stacked together in the depth dimension. We have a dropout layer and the final forward LSTM in the X direction, 256 elements. And this weird code says its output, it's one-dimensional because it's a sequence and it's trained with CTC. And it's got 134 units, which is the size of the character set. And that's all there is to it.
This is something you made up, or is it?
Yes, it's something I made up. If you saw my Tesseract tutorial earlier in the year, you will have seen a similar language, but this is different. Well, partly because TensorFlow has this convention of how the 4 dimensions in the tensor are used, and partly because there was somebody else at Google working with a similar language, and I wanted to make it as compatible as possible with that. So we've ended up with this language for this particular model, and the new Tesseract, when it comes out, I've already started work on adapting it, and it will have the same language, which means that I've had to transpose X and Y in every single network operation in Tesseract, which has taken a while. But it's almost complete. And then there'll be nothing stopping the release of Tesseract after that, apart from the fact that I haven't yet implemented this reshape layer. And I believe I'm near the end, which is good because I'm nearly out of time.
Is the code for that available, or is it going to be available separately, or just?
The code for it will be on the TensorFlow models site. And the nice thing about this language is that you can use it for variable size images too. This specification here says the image size is fixed, but if you specify zeros for either X or Y, it can cope with that, and it will allow that, provided somewhere in here you specify the right network layer to reduce it to a known size. So for instance, if you use a summarizing LSTM layer, you can take an unknown height and convert it to a known size of 1, basically. So the the Tesseract model that I showed you earlier can be implemented using the same code if you give it the right data set. And that's the nice thing about it. It's not just for this data set. So here are the results of this model. Now I trained this model using Google infrastructure, using our parallel training. I used 40 training workers and 5 parameter servers. And within a week, I had this. As you can see, it's pretty good. The word, the word recall is close to 90%, and the entire sequence error is down to just over 25%, which means it gets 75% of every one of those signs right. Completely right. So there's still plenty of room for improvement.
This produces the canonical output.
Yes.
So what are the kind of possible things that can happen there? Are there abbreviations, for example? Are there capitalizations? What is the coping with that?
There are a few abbreviations. Saint
Is learning these abbreviations as well?
Yes. Saint's the only one I can think of that I've seen reasonably frequently. There's another one which escapes my memory at the moment, but I think there's only about two or three that I've seen. And it learns them and it produces the canonical text without any extra engineering help. Apart from the complex engineering that went into designing the model, there is no other engineering required. That's the beauty of it. So here are a couple of failures. That no entry sign has confused it and thinks there's a Q there somehow. And these 3 are so blurry that it was unable to see this. So it's not 100% foolproof at pulling out the best information available from those 4 images. But it does it pretty well most of the time. And this is the Tesseract network description. And that 105 is specific to English. Actually, when you're doing this with Tesseract, it ignores that last number and it just uses the unichar set to generate the size. But it speaks the same language, which is what I wanted to achieve. So if you work with one, you can work with the other. And this is the URL for the data set. I don't have the URL for the code on here, but if you go to TensorFlow models, it's not there yet, but it'll be there very soon as I get that pull request in and get it to work. The data set's not quite there either. That's still uploading apparently. The person uploading it said he couldn't do it because the files are too big for his machine. They are pretty big. We've got the training set is split into 512 shards of 300 megabytes each. It's pretty big. Because those images are not JPEG, you don't want to damage them any further than they have been already in the process of getting to where they are. That's it. Any questions? Yeah.
In the convolutional layers at the beginning, before the LSTM, you have a lot less filters than usually are there. Is there a reason for this, or was it just the maximum you thought was needed?
The maximum I thought was needed because the LSTM itself is able to work out what combinations of filters it wants. And again, this is based on my previous experience with the existence proof that a single LSTM can work with the raw image and learn English. So if it can do that, it doesn't really need very many filters anyway. That's correct, yes, a single letter defines a layer type.
So there is a limit of 52 layer types in general, right?
You just go to more letters if you really want more than that. But I think the language will become... the language would become untenable if it were to get that complicated. It's already complicated enough.
So the only thing which is really hard to there is the 3 lines.
Yes.
So if you can automate this part, you have a good generic layout analysis plus recognition.
Yes, that hadn't escaped my attention. Yes, that's correct.
And what's the way to go there? Is it just counting that you need, or?
Well, LSTMs can do that.
Yeah, exactly.
Yeah, I have an idea in mind.
Stop at 3.
I have an idea in mind for a more generic LSTM-based layout analysis system that would combine with that kind of network to do basically full OCR of at least a paragraph.
And if you have lots of clutter, this learns to discard. So
Yes.
in principle, you would just throw any image in there and just focus on the text areas of money.
In principle, yes.
Assuming that they are horizontal, more or less.
So,
That they are more or less horizontal.
yes, yes, if it's more or less horizontal, that should work fine. Yes. Yes, there's lots of interesting ideas for future research there, definitely. Any more questions? Or is the talk really that crystal clear that you don't have any more questions?
Right, that sounds everybody? Okay, so thank you very much. And visit the website.
Coming soon.
Coming soon.
Thanks.
It was actually very clear.
Good.